Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Triangulation is brought to you by CacheFly at CacheFly.com.
This is Triangulation, episode 146, recorded April 7th, 2014. Jeff Hawkins. Triangulation is brought to you by LegalZoom. Visit LegalZoom.com to save on your legal needs and gain access to a network of legal plan attorneys for guidance. LegalZoom's not a law firm, but provides self-help services at your specific direction. Visit LegalZoom.com and use the offer code Triangulation to get $10 off at checkout. And by Audible.com. To download the free audiobook of your choice, go to audiblepodcast.com/triangulation. It's time for Triangulation, the show I look forward to all week. Of course, it's on a Monday, so it's a very short looking forward to. Because I get to talk to some of the most interesting, the smartest people in the world. And you get to, too. And it is, it's a thrill. It's an opportunity, a privilege to sit down with somebody and talk to them for an hour. We get such great guests. But this is a guy I've actually wanted to interview for a long time, since I read his book about 7 years ago called On Intelligence. Jeff Hawkins is here. And I want to introduce you as the founder of Palm and the Pilot. And I didn't even remember, but I'd interviewed you when the Palm Pilot came out many months ago.
You were the first guy who said, this is going to be big.
I was right. Once in a while I get one. And the creator of graffiti.
Yeah.
But what I found out when I read your book On Intelligence is that was a sideline.
Yeah, it was.
You got distracted.
Well, I really was into, right out of college, I fell in love with brains, and I wanted to study neuroscience, and I wanted to study theory of brains. And it turned out it was really hard to do that back then. You couldn't do it. I mean, it was not hard technically. It was like you couldn't go to school for that. There were no degree programs for that.
There weren't?
No. Hard to believe. I actually became a graduate student at Berkeley, and I wrote a thesis proposal, and they said, this is great, but you can't do it. So after,
what was your thesis proposal?
It was basically on modeling the cortex as a predictive memory system.
And you're doing it today.
I'm doing it today.
You got to write your thesis.
I did in some sense. But I was basically told you can't do that. So, and it was, trust me, this is multiple years getting into that position. It was really kind of, I quit my job in the computing industry, and it was difficult. But I went back in the computing industry, and I thought it would be for about 4 years. And then, I started
pulling,
and it gets very, very difficult to get out of that.
And then Visor, handspring.
Well, look, getting excited about mobile computing, I was one of the first guys up there saying, this, everyone's going to have a mobile computer in your pocket.
And you were right. I mean, this Pilot was a huge hit.
That was a very successful product.
Yeah.
Palm 5 and then the Trio.
And I got a Trio. Wait, but this is my Trio.
That's an early Trio. That's the very early
Yeah.
Trio.
Well, I owned all of these, and I have a few handspring modules lying around.
Gosh, wow.
So I was a fan of the product. One of the things you did I thought was very interesting. I think you talk about this in On Intelligence. Graffiti.
Yeah.
Up to then, all the handwriting recognition attempts had been to get the computer to learn how humans did it.
Yeah.
And that seems like that's what we always, it's their job. We're the boss.
Yeah.
They should learn how we do it. Turns out that's pretty tricky. So you had the insight, which nobody had. Well, why don't we learn, because we learn faster, and do it the computer's way?
And not only can we learn, but people actually like learning things. They like learning things certain things, and not everything, but we like learning new tools. It's kind of fun. And as long as it's rewarding and it's easy and you get to do a new skill, people enjoy it.
So graffiti was very close to the block letter alphabet, but with a few changes.
Very few changes, but that made all the difference.
But you had to learn those. It was the ambiguous characters, right?
Well, sort of, yeah. It was also it was designed to be fast, so you could write really quick, and you had to be able to do it so that you could write the letters right on top of one another.
Right.
So because
you were writing in this very tiny little
we'd write the letters right on top of each other. So we had to make sure that they wouldn't get they would be disambiguated.
Yeah. But it worked really well. It did have a stylus, which Steve Jobs famously mocked, but it worked really well.
Well, back in those days, you couldn't do the touch panel.
Right. In fact, that
technology didn't exist.
Even when Jobs started the iPhone, as we've learned, it was not very easy to do.
Yeah, and this was not easy to do at the time either. So,
really? Yeah.
Oh, yeah. This was a very difficult product to build at the time. We were pushing the limits in many different directions. Hard to believe.
You know, it's funny. I still remember graffiti. I could still do it in my sleep.
Yeah.
So you're right. You do learn that.
Yeah. People like learning things.
Yeah. In fact, I got a device the other day that had graffiti It's still around.
No.
No?
I don't know.
Maybe they're stealing
I
it.
have no idea. Let's be up front here. I haven't done anything in mobile computing for 12 years.
Because you got back to your first
I
love.
went back to brain science, and 12 years ago I started the Redwood Neuroscience Institute. And
what was the point of that?
that was basically a place where people could study theory of neocortex because it was very difficult to do it anywhere. I was talking to some neuroscience friends of mine, and they said, I said, you know, why is it so hard to do this? People won't let you study this. And they said, why don't you start a place to do that? And I go, well, that's crazy. I said, I'll only start an institute if you help me.
Huh.
And they did. So we started, and so that became sort of the mecca for neocortical theory. It's now at Berkeley.
I want to mention a couple other things because you deserve credit for, according to Wikipedia, developing rapid application development, RAD. Is that not fair?
I don't know. I don't know. I did an early product at Grid called Grid Task, which was like that. Maybe that's what we're thinking about. I don't claim any credit for anything. I'm a forward-looking guy.
I like that.
I don't go in the past.
You did not want us to bring up the Palm, but I did anyway.
It's all about the future. I mean, the future is exciting. The past is kind of...
It's actually very exciting. And the brain is ultimately the final frontier.
It is.
You mentioned the neocortex. That's the curly thing.
It's a curly thing on top if you took a skull off, but it's also about 80% of the volume of a human brain. And it's where all high-level intelligence occurs. So your high-level vision, your language, everything you can tell me is stored in the neocortex. All high-level touch, pretty much, other than your basic behaviors and instincts, is in the neocortex.
It's what we think of as mind.
It's what we think of as
consciousness.
Mind. Yes. Pretty much, it's 80% of what we have, and all mammals have one. Non-mammals don't. And of course, we are smart because ours is really big. Our neocortex went. It got so big that it can't fit in your skull anymore. It got all wrinkled, and we have big heads. And
infant mortality skyrocketed.
Exactly. We have to be born, in some sense, prematurely because we can't wait to where brains fully form.
Yeah.
So that's, but, to me, it's the ultimate question. It's like, if you understand humanity, you understand who you are. This is like, and I fell in love with this question right when I was 22 years old. I just, oh my gosh, I just have to work on this. And I felt in my lifetime we would be able to make progress understanding how it works.
And as you pointed out, I think it was in the show, maybe it was before the show. Yes, you did. There wasn't really much knowledge about how the brain worked when you were in school.
Well, there's a lot of details knowledge. There's tons and tons of details, like how the neurons function.
So we knew about synapses. I remember studying that. Synapses, neurons.
But if you ask for overall theory,
like how it works.
Like, what is how does this whole thing work? What are these hundreds of,
we can see it structurally, but we can't figure out
what
that's
right. So what got me going was there was this issue of Scientific American in 1979, September, which was dedicated to the brain.
Right, I remember it.
Yeah,
I remember the cover.
It was a famous issue, actually.
Yeah.
A lot of neuroscientists got started because of that. And they talked about all these aspects of the brain, and the very last story was by Francis Crick of DNA fame. Mm-hmm. And Francis said, you know what? It was like, he basically said, we have no idea how this works. So everyone's talking about all these details, but we're lacking a framework. There's no theoretical framework for understanding this. And I said, well, he's right. A lot of details, but no theory. No big theory. It was a lot of little things. So if you ask someone, what does the brain do and how does it work? I was like, I don't know. So,
isn't that amazing? I mean, as late as 1979.
It's still today like that for many people. We're making good progress now, but it's amazing how much research is published on neuroscience and how yet it's considered a big unsolved problem.
So when I was in school, we said that we learned by forming connections in the mind with the synapses, the dendrites.
Yeah.
I'm kind of very vague on this.
Yeah.
Do we still think that?
Well, the classic theory is that memory is formed by the strengthening and weakening of these connections between cells, called synapses. What we've learned in the last 10 or 15 years, which hasn't really permeated through most people's theories yet, but it's not just the strengthening of the connections, but the brain makes new ones all the time. It's growing these, you can actually watch little movies of them, growing these connections between two cells that didn't exist before.
That's exciting because it means that we're not limited to what we've got.
That's right. And far more information can be stored by forming new connections between cells than just strengthening and weakening the old ones. And we also know those connections are very, very unreliable. So if you looked at a synapse in a brain between neuron 1 and neuron 2, they form this connection. It's not a precision thing. It's noisy. It's unreliable. Sometimes it works. Sometimes it doesn't work. There's like this. The brain is full of all these noisy elements. So you can't rely on a synapse having any kind of precision to it. But you can make a lot of new connections, and that's a great way of going. Anyway, so we think we understand how that works now, how memories are formed by not just the mechanism, but we have theories about how the memory structures are formed.
How do we get this information? Is it through functional MRIs?
Neuroscience is one of the largest fields of science these days.
Is it? Oh, good. Well, that's
my
encouraging.
Goodness. If you go to the annual Society for Neuroscience conference, there's something around 30,000 scientists show up in that. I mean, this is in the U.S. That's huge. There are dozens of journals, thousands of papers published every year. So there's tons and tons of data, many different techniques for getting them, and they're inventing new ones all the time. The problem is that almost all the data is unassimilated. It's very, very few.
This is kind of the story of life today, right?
Well, I don't know. It's the
Maybe
story
you're going to solve this.
It's the story of science.
Right.
I mean,
we're getting really good at getting the data points.
We are, and yet, almost all neuroscientists would say, we have no idea how this thing works.
Interesting.
But we're starting, my company is at the forefront of this, and we're starting to make some really excellent progress understanding in detail how the whole thing works. And
is there consensus about this, or is this a hotly debated topic?
I wouldn't say it's hotly debated. I don't think there's consensus. Clearly not consensus. But there are camps, and they are growing and moving about and changing.
It's science. That makes sense.
Yeah. So, I mean, we're not loners out in the woods here. Our work is highly respected by many people. There's other people who disagree and have different opinions. But in my company, I'm doing this in a different structure. We're doing this in a business, but we're very open about it.
You actually said an interesting thing in your Google talk, which everybody should watch. You said it's got to be a product.
Well,
it's important that it be a deliverable product that makes money as a business.
There's multiple ways of getting people excited about something.
Right.
And there's people who are excited about brain theory just because it's interesting scientific stuff. But there's a lot of people who get excited about something when they see it as a technology or they see it as a way of making a livelihood.
Yeah.
So if I want people around the world to study brain theory, understand how brains work, well, one great way of doing that is show them how they can build businesses on it.
Yeah.
And also building something is a ultimate proof. You can't get something to work. You can come up with theories and you can postulate, but I think it was Carver Mead who basically said, you don't really understand something until you built it. And there's some truth to that. You can have all the theories in the world, but until you actually try to build these things and make them work, you don't quite understand exactly what's going on. So for us, that's sort of a complement to the theories. Like, okay, we should implement the stuff. It should work, and it shouldn't work on trivial things. It shouldn't work on toy problems. It should work on real things.
Yeah.
And
if it does work, that's a proof. It's a proof of
well, it's a
concept.
proof that it works, and then we have to. It's a way of getting more people to give credence to that particular idea. And I think it's it's also the beginning. I think you interviewed. It was Jack Clark, I think it was recently. Or not you, it was Mike did that, a different show. But anyway.
He was talking about Numenta.
Yeah, and there was a story about me recently that came out in the Register. And he got one of the things he picked up in the story, which I think was great, was there's a question in the whole machine intelligence, machine learning world about what does the role of brain science have? And how interesting is brain science? And how important is it? And so that's controversial about, do you need to understand how brains work to build machine intelligence? I think you do. And so I think we're also on a path to machine intelligence, and so that's something we have to build. And so we need to get down that path. We need to start down there today.
Well, now that's an interesting question. I want to take a break. When we come back, machines versus man, deterministic kind of von Neumann devices versus this kind of failure-ridden kind of wetware.
Yeah, okay.
Let's talk about how we can mix the two in just a second. Jeff Hawkins is our guest, the man who created the Palm Pilot. His company, Numenta, is working on creating first software and eventually hardware that works similarly to the brain. Would you say exactly the same or similarly?
That's not a short answer.
Okay, we'll do that. We'll do that long answer in a second. Our show today is brought to you by our friends at LegalZoom.com. It is time to start your own business, and I think this is a great place to do it. When we first started Twit, of course, actually wasn't everybody. My friend Kevin Rose, the parasite, said that you should. That's another story for another day. You should. By the way, if you missed Twit on Sunday yesterday, Kevin was on, and actually, Kevin's very good about this whole thing, better than I am. And anyway, he said you should get an LLC to protect yourself. And that was just me. I couldn't afford a law firm. What did I do? I went to LegalZoom.com for $99, plus the filing fees, of course. You can get started, create your own LLC. We're still running under those original organization papers. You can also do a Chapter S or a C Corp. We also trademarked our brand. Of course, you got to do that. $169. And also for your family, your last will and testament. You can set up trusts, your durable power of attorney, your medical power of attorney, healthcare power of attorney. Very important to have that. All at LegalZoom.com for very affordable prices. Now, it did come up. Why LLC versus an S Corp? Or what state should I set it up in? And I just kind of guessed. Turns out I didn't guess badly. But now at LegalZoom, you can get help from a legal plan attorney. Now, and we're not talking $350 an hour either. They've pre-negotiated prices with an attorney in your state. You could check the attorney's profile, read unedited reviews from customers, pick the attorney that's right for you, get great advice at a very affordable price. I mean, they really have figured this all out. LegalZoom.com. They're not a law firm. Don't mistake that. They provide self-help services at your specific directions and can set you up with their network of legal plan attorneys for guidance. Don't put off all those things that can help you get started in business, protect your family. Go to LegalZoom.com. Use our offer code Triangulation. Let them know you heard about it on Triangulation, and they'll give you $10 off at checkout. LegalZoom.com. You say, we're talking to Jeff Hawkins, a guy I've wanted to talk to ever since I read his book on intelligence, which got me so excited. Turns out I'd talked to you before about this thing, this Palm thing. That I don't know whatever happened to that. But actually, you must, I have to say, when you saw smartphones emerge and stuff, it must have been a validation that you were on the right track.
Oh, wait, there was no question.
You were right.
Well, there's no question we were on, we were
This
in
was
the
a
middle
huge
of
success.
That was a huge success. We had a lot of success in the smartphone space, too.
Trios,
the Trio 600 was a great, sold millions of those.
I loved my Trio 600.
Millions of those.
This
anyway,
one, I don't know what this one is. That was
an organizer. Oh, it's a long story.
This was not a phone.
That was not a phone.
But it looks like
it looked like a phone. There was a phone that looked just like that.
I have that, too, somewhere.
I think that's the non-phone version. But
I owned them all. No, it is the phone version.
Is it?
It's got a little phone on it.
Oh, well, then it is the phone.
It's got a little phone
all
thing
right.
on it.
I don't remember.
I could make a call if Singular still existed. Meanwhile, we think of, it was, of course, Alan Turing who kind of gave us our knowledge, our understanding of how, he didn't even ever build it, but he thought about building this Turing machine and gave us the Turing test for determining whether a computer was, artificial intelligence had succeeded. You say that's a bad test.
Oh, it is a bad test. I don't think we should. First of all, I'm very interested in building intelligent machines, and we're working on that. But I don't think the goal should be to emulate a human. And I don't think that's where it's going to be on. It's not about building, humanoid robots that we talk to and sit and have coffee with. You can take the principles by which the brain works and build machines that are undoubtedly intelligent but not human-like at all. And so Turing, by going down the Turing test, set us down this path of thinking, oh, intelligent machines have to talk to us and they have to converse about human-like things. And it's just the wrong goal. And I think it was because, if you read what Turing wrote about it, he didn't want to get in arguments about whether it was possible. So he just came up with this test to say, like, don't argue with me about, whether it's possible to build intelligent machines. But unfortunately, I think it's put us down the wrong path in terms of thinking about what intelligent machines are going to be like.
They're not going to be like us.
Well, at least not most of them. I'm not trying to say couldn't build something like that, but certainly not for many, many years. But that shouldn't be the goal.
Right.
The goal should be building machines that learn. What you mentioned, Turing, he basically set the paradigm in place for the next 80 years.
Right.
It was in 1935 he wrote that original paper. And, but, that's a programming paradigm. That's like putting the logic in formal languages and running algorithms. But brains are memory machines. They're learning machines. Right. And we've never really mastered that. We've tried
to shoehorn learning into these Turing devices.
Right? Yeah. So the whole, AI and all the neural networks and all the stuff. And what it really basically comes down to is we have to really understand how the brain works and how it learns.
Come from the other direction.
Yeah. Well, and this is a hot topic, by the way. And I gave a talk a year ago at several conferences related to semiconductors. And all the semiconductor researchers are looking what they call post-von Neumann. What's next? And where do we go? And they see the limits of Moore's law. And so there's a lot of convergence of people saying, what's the next 80 years is going to be about. And most people think it's about learning machines.
Well, why should biology drive this? I mean, evolution is a kind of a random walk that happened to work, and is that the best way?
I don't know, but
I mean, it's one way. It's our way.
I mean, it is one way, and I think for me, my logic was the following, and I think it's held up well. Is we have one example of an intelligent machine.
One.
We have one. And in the early AI, I mean, you know, when I got into this field in the beginning 80s, at that point, there'd already been 30 years of AI.
Right.
And it had gone nowhere. So you might sit there and go, maybe that didn't work. What should we look at? And it was obvious to me, let's look at brains. That's my point is we don't have to build a brain. We don't have to build a human brain. We just have to understand how it works.
Right.
And when you understand how it works, then you can say, okay, I've got a whole new set of tools here. Just like Turing said, I have an idea. He didn't say how to build computers. Once we have this idea about exactly how brains work, then we can do variations on them. We can make all kinds of amazing stuff that we couldn't even think about.
It's just a starting point, in other words.
It's a starting point. And it's not, but it turns out that the way the brain works is really, really clever.
And very, very different.
It's very, very different, and it's fascinating when you start to understand in detail how it works. Because you go, oh my gosh, I can see why it's so different, why other approaches wouldn't work. We're at that stage now where we understand enough about it, where it's very clear that there are certain principles that you just cannot get away from, that you'll never be successful unless you accept some of these principles.
So the computer uses what you call a dense representation of data.
Yeah.
And I'm going to see if we can do this.
Yeah.
Without slides, without a whiteboard.
Yeah.
But the computer, if you use as an example the ASCII table of characters.
Yeah.
Some arbitrary person says this is what the binary representation of the letter M is, and that's what it is, and we all agree. And it doesn't have to be that, but it is.
Yes, it was an arbitrary assignment.
Yep.
And it's dense because, well, that term is sometimes used, I use it, because if you look at like a byte or a word in computer memory, we try to use all possible combinations.
Right.
So a byte has 256 combinations, and we try to use them all.
Right.
So every possible combination is used. It's dense from all zeros to all ones.
But no one bit in that byte has any meaning at all.
That's right. Well, you could say it's the 2-bit or the 4-bit. But if I ask you, here's a letter from the alphabet in ASCII, and I say, what does the 3rd bit mean? It's like,
doesn't tell you anything.
In fact, if you change 1 bit, the entire character is completely different.
Right.
Which is a very efficient way for a computer to manipulate memory. With memory's in short supply, and you're trying to allocate as many, get as much data through as few bits as possible. But it turns out brains don't use that representation at all, and for very good reason. It turns out that in brains,
brittle.
What's that?
It's a brittle representation.
Well, it is brittle, right? Exactly. If you change 1 bit in an ASCII code, totally different.
Right. That wouldn't work so well in the brain.
That wouldn't, right? Because neurons are noisy and synapses are noisy and so on.
It's a messy thing.
But it's not just redundant. The brain isn't just redundant. It's not like just to put some extras there for fault tolerance. The brains use what's called a sparse representation or sparse distributed representation. And you can imagine it being a bit is like a cell. It's either on or an off. And so you can have millions of bits or thousands of bits. And the cells, most of them are inactive at any point in time. If you looked in your brain right now, most of the cells are not doing anything. Mm-hmm. There's a few, very small percentage are doing something. And they change over time. That's why it's sparse. Very few ones, mostly zeros, very few cells active, mostly inactive. And the bits mean something. They have semantic meaning. They're learned. No one programs it. And so when I want to form a representation of something in a brain, it picks the few percentage of bits that have the right, as a combination, have the right representation. So they're overlapping, but it's essentially the meaning of something is stored in the representation itself. It's not in some table or looked up or some human. It's actually coded in the representation. So
a synapse is not a pointer to the information. It is the information.
It is the information, or the cell's activity is part of the information. It's like this cell might be represent, if I was looking at a face, it might be, something that's nose-like.
Right.
And I have thousands and thousands of cells that are active, most of them are inactive, and they all are together will define, this is Leo Laporte's face.
Right. We talked last week about fMRIs that could actually see a dream. They would show people pictures, and they could see in the brain the kind of very fuzzy but rough representation of that image.
Well, that's right.
That's mind-boggling.
It's a little complex because when you get a little further up in the brain, you can't do that. But the very first parts you can. But anyway, so this is one of the most fundamental differences between brains and computers, is how information is represented.
Right.
And you know, I've stated this, I'll state it right here again. In the future, intelligent machines have to be built on sparse distributed representation.
They're not going to be these von Neumann devices.
We can emulate, we can simulate a brain-like mechanism on a von Neumann computer, but the information structures themselves have to be. So, like, we model brains in our work at Numenta. We build brain models all the time. We're using them in a product called Grok. But in those models, those brain models,
they're on von Neumann machines.
They are, but there's 64,000 neurons. They have sparse distributed representation, so you can model anything.
Right.
Remember, Turing said it's a universal machine.
It is.
So you can model a brain with a von Neumann architecture. However, the thing you have to be modeling has to be sparse distributed memory, and you still have to train it. You can't program in the memory. You have to. Our models, our simulations, you have to train them. You have to feed data, and then it has to experience the world and build a model of the world.
So you also build a sensorium. How do you get data into it?
Well, right now,
you're emulating a cochlea.
Yeah, well,
I love that. So, is that right?
Well, a little bit. So we have two parts of our business. There's a theory part, and we've done a lot of things on the theory side and tested the theory. And then there's a product side of the product. Grok is a product. Grok, we take data from machines, computers, basically, servers. And at Grok today, we just introduced it less than 2 weeks ago. And it runs on Amazon's AWS marketplace, and you can use it with Amazon's AWS servers. And we stream data from all kinds of metrics off of computers that people run on Amazon, and we feed them into Grok, and Grok builds a model of them. And I make the analogy, it's a little bit like listening to music. So some data's coming in, and it's just some variable over time changing pattern, and we discover the temporal patterns in it. We learn what that data normally sounds like, if you will, and how accurate it is, and how good a musician this is. And so we can detect very subtle changes in data coming off of computers. It can be very noisy data. It can be partly stochastic. It doesn't have to be. It's not like a sine wave. It's a really crazy data. But we can still discover the structure in it, and we can detect when it has become different. So the brain makes a model and makes predictions and detects anomalies. Well, we can model that, and we can detect when there's anomalies in data streams.
You're using it to monitor machinery, to monitor energy usage? We
do a lot of things with it. The first instance of Grok is basically monitoring computers running on Amazon's AWS. So if you're, half the web runs on Amazon.
Absolutely.
More than half, probably. Yeah. I don't know how much. But those servers have to be maintained. People have to know when the software is running well or not running well, when problems are occurring in the applications they're running on those servers. So we can do a great job of detecting when, in a very, very subtle and sophisticated way, when something that is running on a cloud infrastructure like AWS, when it's acting weird or different.
About to fail, in other words.
Well, I won't even say it's about to fail. Sometimes they're good things. Sometimes you discover that there's some unusual trend in your e-commerce site, and that's something you want to find out. It's like, hey, my customers are acting differently.
Right.
Sometimes it was like, I've put out a new push of code, and it's a new version of this application, and it's starting to act a little wonky. It may not fail, but it may not be as efficient as before, or just maybe not behaving the way you thought it would be. So it's not about computers failing, because the whole point of a cloud infrastructure is that you can just kill one and start another one.
Right.
It's more about monitoring the health of these things,
and
knowing when something unusual, either good or bad, is about to happen.
You've also used it, although it doesn't look like you're using it this way, to predict things.
We do. We did. We started with this remember it started as a science of brains, then we built a technology base on that, and now we built a product. So when we were trying to figure out what product to build, we applied the technology to lots of things. We were predicting energy usage in buildings.
Effectively, too.
Yes, very good. We were really good at this. In fact, we were able to predict energy pricing, energy usage on a building at a room level. We were predicting, basically product demands on a daily basis or even an hourly basis. There was a lot of things we could do. It turns out, though, interesting, when you make a prediction, like every hour or every 15 minutes, and you can predict what's going to happen every 15 minutes for the next day, you have to be able to act on that prediction.
Right.
And most companies are not in a position to act on it. So we could say there's a
we know
whole,
what's going to happen.
Well,
you can't do anything about it.
there's a whole field of energy called demand response.
Yeah.
Where the idea is that if you know how much energy you're going to consume over the next few hours, and you know what the pricing is going to be because you can get variable pricing, then you could automate. You know, like a pre-cool,
buy low.
But yeah, well, buy low, pre-cool a building, or wait a little bit later. Various things you can do. You know, cut back, do another manufacturing lot tomorrow as opposed to today. So this is a really great idea, but it turns out very, very few people are actually able to do it. So if you can say, here's what your energy consumption is going to be, then you say, yeah, but we're not really set up to do that.
Information. So what are they going to?
Well, you need to automate it.
Right.
You need to automate it. So anyway, we moved away from prediction because that'll come later. But we worked on anomaly detection, which is just a flip side of prediction.
Right.
Like, okay, I have a prediction, and how different is it turn out? And it turns out that today you can do great products with anomaly detection because we can present all this information to a user on a mobile device, and they can look and we can monitor, let's say, 100 servers. And we can say, you know, these two are the ones that are acting weird right now, and here's why. And you can look into it. So
does this validate the model?
Oh, I mean, from the neuroscience
your brain.
Well, it validates its utility. Absolutely. It doesn't prove that we got the brain science right. But
it works.
It works. I'm pretty certain we have the brain science right. I'm very confident. But that'll come.
But this is the brain of like a little tiny lizard at this point.
It's
a cricket.
Well, it's modeling the section of the neocortex. It's only mammals, so lizards wouldn't have it.
We're out,
I'll give you how small it is. It's about 1/1,000,000th the size of a human brain, and about 1,000th the size of a mouse neocortex.
That ain't bad.
Thousandth the size.
You're within a few orders of magnitude. You're getting there.
We're getting. It's validating the technology.
Yeah,
and
absolutely.
It turns out that you take 100,000 neurons. They're very, very powerful, actually.
Right.
That's why you and I have such amazing memory. We do an incredible number of things. So even a very small, teeny part of that is pretty cool.
That's really amazing. And there's no reason you couldn't scale it, right?
No reason, although there are issues. There are reasons, actually, why you can't scale it.
Why can't you?
Well, to scale it to, let's say, even the mouse size, 1,000 times bigger, requires, well, the software would be too slow. So let's say today we've done a huge amount of software optimization, and we can do one inference prediction step in about 50 milliseconds. So I go 1,000 times that.
That's pretty fast.
Yeah, it's pretty slow, right? You know,
it's too slow for the brain.
It's too slow to do anything useful with it.
But the brain isn't that fast. It's massively parallel. Is that?
Yeah. Well, you don't. If you're simulating on a computer with software, it's hard. If you were to build custom hardware for this, then it's easy. And this is why there's we're working with a number of people now who are very actively pursuing hardware implementation.
That would be the next step.
Yes. It's clear, I mentioned earlier how a lot of people are looking for post-von Neumann. Well, some of them are acting on it. There's quite a lot of interest in our algorithms.
Would they be ASICs? Or how?
I don't, it's not my field.
Right.
I'm a double E, but that's not my field. There is, if we think about this, I know of at least 4 teams now who are actively pursuing, and I'm sure there's more, actively pursuing modeling memory structures very, very similar or exactly what we do, so based on our work. And they have very different ideas how they're going to do that. So what is the future of brain hardware going to look like? It's hard to know. If you haven't been to go to the Computer History Museum down in...
so cool.
It is very cool. But one thing that's surprising, people don't realize, in the beginning of building computers, there was a lot of unknown how to do this. So how do you implement memory?
Right.
They use mercury delay lines. They use
magnetic cores with...
They use video screens as a memory device. Look, it was hard. We can laugh at it, but it was really hard.
Oh, yeah, sure.
So we're going to go through the same sort of evolutionary thing going on now.
Yeah.
I know people who think they're going to use on-chip photonics, meaning using light channels. There are people looking at different types of memory structures. Here's one of the cool things about all this. We mentioned earlier how the brain is not really very reliable, the elements. The individual elements are not very reliable. So in computers today, every element has to work exactly.
Right.
If you can say, all right, well, 1% of my memory elements don't have to be very reliable, you can make them so much more dense. And you can pack them in there, and you can run them at different types of speeds. And so it opens up a whole new world of possibilities for... Literally, I think it's going to be the next 70 years of innovation in computer hardware. Much of it's going to be driven by these kind of memory structures, these learning computers.
You have to throw out everything we know, though, and start from...
Well, you start from that base, and then you build on it. But it opens up... Imagine all of a sudden you tell to a computer designer, well, you're allowed to have a certain % of failures. throughout
That's a very different model.
It is, because today, basically, computer chips have to be flawless. Perfect.
Yeah.
So a lot of people are excited about this sort of. So I don't know how it's going to play out. But I understand, what we do understand pretty well is some of the principles of how it's going to have to work. And then what's the best way of implementing them today is unknown.
We're talking to Jeff Hawkins. His company, Numenta, has a product. You can get it for free. It's open source. There's also a paid version called Grok at Numenta.com. And it's on the Amazon Marketplace. And you can play with it. Have high-frequency traders approached you for this?
We've talked, yes, they have.
I can see that they would be, all those quants on Wall Street are going.
You know, there's, I think, was it Mike Lewis has a new book on this, right? It turns out that where all they're making their money these days is not on intelligence or analytics or discovering patterns. It's speed. It's speed.
Isn't that sad?
It is sad.
They're not making anything.
They're basically figuring out how to make a faster pipe than someone else, and then stealing some bits, stealing a few dollars along the way. It doesn't make me very happy.
Reminds me of the Sting, frankly.
Yeah. But there are people. We did a test for some people in the financial world where we were trying to predict trading volumes. So as opposed to trading prices. And actually we did very well with that.
I bet.
We did really well with that. I mean, trying to predict like every 5, 10, 15 minutes or an hour out, what would the volumes of something be. It's not as valuable as predicting like stock prices, but we're not going to, I don't think you can. I actually don't think you can predict stock prices. There's too many people in that market competing with it.
It's too chaotic.
It's too the underlying causes are going to be too hidden.
Right.
There's just too. So where we excel.
But you don't. But this model doesn't care about causes at all, right? I mean, it's just looking at.
But there has to be,
it learns from the past.
There has to be patterns.
But there has to be patterns. Okay.
Imagine this. Imagine I go back to the music analogy, right? Yeah. So you listen to someone play a violin or something like that, and you'll pick up, here's the songs they're playing, here's how often they make a mistake, here's how much they improvise. I can't always predict, but I get a good sense of it. We do really well at that. If you have a couple people playing at the same time, we can do well at that. But imagine the stock market is more like 5,000 people playing 5,000 different instruments all at the same time.
It's chaotic.
And you can't. The overall pattern is going to be lost.
So weather prediction would be difficult.
No, not necessarily. Anyway, weather is something that's very well solved by classic engineering solutions.
Okay, so it is deterministic.
I'm not sure if it's deterministic, but they've got good solutions for. It's not deterministic, but where we excel is where the future of data and the future of analytics is that it really goes back to the Internet of Things. Okay, so imagine. Everything in the world is going to collect data. Your refrigerator, the door, this camera. I mean, everything's collecting data all the time. And they're streaming it someplace. Who's going to do something with that? Right now, it's either thrown away or stuck in some big warehouse.
The NSA saves it in case we can do something with it later.
You really need to model it in real time. You need to be able to send all those data streams to some model that says, I'm going to either act on this or I'm going to detect when something's odd going on.
And the brain, that's what the brain does.
That's right.
It's a prediction machine.
It is.
It takes a stream, builds models, uses that model down the road to predict future behavior.
And it throws away the data. You don't keep the original data.
No, you just keep the model.
You keep the model.
And you know that there is, as you explained, a hall. There's a door on the left, a door on the right. You're turning the knob on the left.
Yep.
It's all because of that model.
This model. So this is what the future of data is, and this is how our stuff works, how Grok works. We don't save the data.
You throw it out.
We every time a new data point arrives, we learn from it, we toss it, and we go on. We make a prediction and inference. So this is the future of data where you're essentially going to stream from, don't ask me for a date, but literally billions of sources of data.
Right. Because everything's smart, everything's
connected, and there's going to be huge opportunity for people to figure out how do I make things more efficient, how do I save energy, how do I save cost, how do I detect when things are about to fail, how do I find new market opportunities in this data. And today we do with data scientists looking at pouring through data that's been collected. In the future, it's all going to be streaming.
Yeah.
And that's what we're focused on.
Yeah, that makes a lot of sense. It's the only way to handle it.
It really is. It's really the only way. But it's not where the industry is today.
Right.
Today, that's where Grok is. That's what we're doing. So we're focused purely on streaming data, and the technical term is online learning, meaning you learn every single moment. It's not like you batch it up and say, okay, build a model. It's like you're learning continuously, and you're forgetting continuously too. It's constantly learning, constantly forgetting.
Jeff we're going to have a little more with Jeff. I'll give you a chance to ask your questions in just a second. I've mentioned a couple of times Jeff's book on intelligence. I do recommend it. I know things have changed a little bit since you wrote it. Isn't that amazing?
With new stuff. The book is still valid.
Nothing you said was wrong.
One teeny little thing I would change, but beyond that, no.
I'll tell you what, I've always been fascinated by this. It's the first book I read that gave me what I considered a working understanding of the brain and its function. And I'd never read anything like this before. It's really phenomenal. And you can get it free right now from audible.com. We're going to tell you how to get this absolutely free. Now, I should say, in fairness, there are 150,000 books. There's lots of choices. It doesn't have to be nonfiction. Classics, thrillers, science fiction. It's the best science fiction collection ever. I joined Audible in 2000, and it had a very sparse science fiction library. I was very disappointed because that's what I wanted to hear. And Audible was disappointed by that. And I know that's one of the first things they did is they built their studio. They have 9 recording studios in their offices in Newark, and they called it Audible Frontiers, started recording audio versions of the classics that had never been made in audiobooks and new stuff as it was coming in. They now have the best selection of science fiction. If you love sci-fi, you will love listening to these books. They come alive in your mind. It's better than anything any Tom Cruise movie could ever do. You read the Philip K. Dick, it's gonna leap to life in your brain. It's a movie in your mind. Go to audiblepodcast.com/triangulation. Sign up for the gold account. Your first month is free. That means your first book is free. You can cancel anytime in that first 30 days, pay nothing. You will also get, besides that first book, the daily digest of the New York Times or the Wall Street Journal in audio. So, this is a really great use of your time in the car. I don't go to the gym anymore without my audiobooks. In fact, if I get there and I don't have my audiobook, I go home. That's it. No workout today. And can I recommend you read this on intelligence? If you enjoy what we're talking about today, this will give you the groundwork. You see, it's in my library. This will give you the groundwork for everything that is about to happen, the brave new world that's ahead. audiblepodcast.com/triangulation. So let's talk a little bit about what is ahead, Jeff Hawkins. Based on what obviously, Grok is just the first baby steps in this.
It is. Yeah.
But in this journey, it's funny, I'm watching your Google Talk, and there comes Ray Kurzweil to the microphone. I thought, oh my God, this is going to be interesting. Because he's the guy who says, I'm going to download my brain. Yeah. I'm going to live long enough to live forever. Yeah. You don't think that's going to happen?
I don't think you're going to download your brain.
Why not?
Well,
please.
Well, hang on a second. I think the future is going to be fantastic.
Oh yeah.
So don't let me. I'm not like raining on this future here, right?
Okay.
There are going to be unbelievable things that happen in intelligent machines in the future. So it's a really exciting.
Okay, you and I are the same age. In our lifetime?
That's questionable.
Damn it.
Look, it's already starting to happen.
In our kids' lifetime.
Oh, absolutely, absolutely. If you believe Ray Kurzweil, things are accelerating so much, it's all going to happen.
Yeah, we're right at the elbow.
In 5 years, it's all over. But
yeah.
But
I think not. Because he said that a while ago, and it still hasn't happened.
If I live another 30 years, let's hope, we'll see some really cool stuff.
Yeah.
But the computers have been around for 70, 80 years, and they're still getting cooler.
Yeah.
So this is not something that's going to happen and go away. This is really the future of machine computing.
We live in amazing times, and I'm not saying I wish it were happening faster. It's I can barely keep up as it is.
So anyway, really exciting future. We can talk about that. The downloading your brain part. It's not that I'm not a fan of it. I just don't think it's going to be it's going to happen. I don't
Is
think
it technically hard?
I think it's technically almost impossible. You never want to say anything's truly, truly impossible.
Well, for one thing, even if you get the whole neocortex, that's not you.
Well, if you could get
your memories.
You'd have to get the entire brain plus all of your memories. But here's the problem. Here's the real problem.
There's no limbic system. There's no emotion.
Well, you'd have to replicate all of that.
Right.
You'd have to replicate everything.
Okay.
Okay. Yes, and every experience you've ever had would have to be. But the problem really is.
And it's still not you. It's just something.
Well, no, it's like I'm not a big sci-fi person, but it's like in the Matrix. In theory, we all thought of that as a kid. Hey, if I could just plug in the right stream, it would work, right?
I like your impression of Keanu Reeves in the Google Talk is quite good. I don't know if they caught that. You went, whoa.
So
that was good.
Here's why it might be so hard it'll never happen, and we can argue whether people really will want to have it happen. Let's talk about that in a second.
Yes.
But it turns out that the memory in the brain is not something you can extract. It's physically, it's tied. It's only meaningful in the context of the exact timing of the connections.
You'd need to recreate the stream.
Yeah, you'd have to recreate the delays in every axon.
Yeah.
You know, if a cubic millimeter, you know how small that is?
Yeah.
That's like nothing.
Head of a pin.
That's got something like about 100,000 neurons in it or something like that. Well, you know, synapses. I mean, thousands of kilometers of wiring. I mean, it's unbelievable.
Right.
This is not something you're just going to like take a picture of and say, recreate this, please.
It's difficult.
And then you'd have to recreate all that stuff. I also think it would be a very unsatisfying experience. Imagine if we could do it right now.
Okay.
Okay.
I got a jar.
Mr. Laporte, we're gonna make this your new. This is you.
Wow,
this is the new you, right?
Yes.
It's got high speed in it. So, all right, ready?
Yes.
Zoom. Here it is. Okay. Now this thing starts talking. It says, "Hey, I'm
Wait
Leo.
a minute.
I'm
still here.
I'm over here. You can get rid of that guy."
What? No.
That's my old body.
I'm not done yet.
No, but that's the old body. Trust me, I have everything here.
Oh, Lord.
You don't need.
But it isn't me, and that's the point. There's still a locus.
There's two of you.
There's
I
two.
think, if you want to get into philosophy, I think there'd be two of you, but you wouldn't be very satisfying for you.
Ray always says, I ask him this, and he always says, well, you can't tell, so what does it matter? It's like, well, that does matter.
Well, but my point is, what if it's not like I'm taking you and sucking you out of this body and putting you here. I'm replicating
You're
it.
duplicating it.
And now how would
Even if you could.
Imagine if I had two twins. And I said to one of the twins, well, one of you I got right here. We can just,
I don't need another.
Well, we get rid of you. You're
Right.
just taking too much food and energy right now. How would you feel if you had the other one?
And then in the next second, they start diverging and diverging and diverging. So,
Yeah. So I think there's two issues here. One, I don't think it would be very satisfactory. I think people imagine like I'm on my deathbed and my last breath I get transferred.
Right.
But that's not the real problem. The real problem is it's physically going to be, I will say, as close to impossible as I can imagine. Never say nothing is impossible.
But it is likely that we are going to be able to create something that would pass the Turing test. That would seem
almost certainly we'll be able to do that. But I don't think that's where the exciting part in the future of brains is. You know, again, passing the Turing test is making human-like things.
Right.
You know, people thought when the steam engine was invented, it was the beginning of mechanized power, right? Mm-hmm. They originally thought, oh, we're going to build human-like things like robots. That's where the robots came from, right? Back then.
Yep.
But that's not where power went, did it? I mean, we now have cars and little machines that do everything, and this room in here probably has thousands of little motors all over the place.
Right.
The future of mechanized power wasn't robots.
Right.
And the future of super intelligent machines is not humanoid machines. Yes, could you do that? You could, but
it's a lot of work for
well, you know, but the financial and the societal benefits are going to be in other places.
Well, give me an example then of what one of these things might be.
All right, I can speculate, but it's really dangerous to do so. Imagine going back in 1950 and saying, well, okay, well, tell me all the uses of computers are going to be. It's like, no way you're going to get that, right? Come on, I'm smart enough to know that there's no way I'm going to get that. I prefer to talk about the properties. Okay?
All right, let's do that then.
So, for example, we can make brains, artificial brains, that are at least 1 million times faster than human brains, that can think 1 million times faster. Your brain and my brain is made up of pretty slow elements. A neuron can't really do anything less than 5 milliseconds.
Isn't that amazing?
It is amazing.
Yeah.
Right. But we can make silicon much faster.
Right.
Okay, that's one thing. There's no reason why we can't make artificial brains that are bigger than human brains.
Right.
I don't see any reason for that.
But does bigger mean smarter?
Not necessarily.
Yeah.
You know, an elephant has a bigger brain, but it's not necessarily smarter, right? So, but it could be smarter.
Right.
To me, the most exciting thing about artificial brains is, in addition to those things, is they can interface to the world through a different set of senses. We are limited to our senses, and our senses work at a certain speed, and they work in certain, like we only see certain types of light, and we only can feel certain types of, forces in the world. But there's, the world of artificial brains are not going to be limited that way at all. They could have the distributed sensors around the world. They could have three-dimensional sensors. It boggles the mind to think about this. And so you take these combinations of like super fast, super capacity, interface to all kinds of other stuff. By the way, that we can send them into outer space. Humans can't really travel, but we could send artificial brains.
You bet.
So if we want to explore the universe, it's going to be through artificial brains. It's not going to be, us traveling.
Right.
So, but I don't really, within those parameters, I'm not going to speculate what's going to happen. All I can say is it's going to be unbelievable.
Yeah. Is it threatening? Do you worry about Skynet?
I think about it enough to convince myself it's not threatening at all. There's only one thing we should really worry about, really worry about, and that's self-replication. Anything that can replicate itself, whether it's a biological virus or a computer virus or anything, that, once it starts replicating, that's the genie out of the bottle type of thing.
Absolutely.
Right?
But isn't that what would happen? Is that we might start using these to design better and better?
No, I don't. But that's not going to happen at all. Intelligence is, obviously, we use intelligence as humans to help us replicate more.
Right.
But
that's how we got here.
Well, right. But my neocortex is about modeling the world. And I don't have to put a brain into something that replicates. First of all, I don't even know how to do that.
In fact, you might caution against
that.
that.
Probably caution against it. I mean, but look.
This might be a new rule.
But the things that have killed the most humans are viruses.
Right. They replicate.
They replicate. So the simplest things that are small and replicate are the most dangerous. Humans were a threat, not nearly as much of a threat as some virus that's going to come around. How many people died in 1918?
Yeah,
whatever it was,
that's right. The pandemic.
So those are the things we've got to worry about. And building intelligence. Okay, yes, someone could try to make intelligent machines that replicate. I mean, that's not going to happen. And if it is, it's going to be minor. But anyway, intelligence itself is not the threat.
Right.
It's replication, and people have trouble separating those two issues. So,
but that's a caution. That is a caution. If you can do it, folks, and we're talking to the future, don't. Don't, please. Replication's out. Anything else you want to do?
Yeah.
Well, for instance, speech recognition, handwriting recognition, notoriously terrible.
Yeah.
But this could be exactly the category of problems
it could be
easily solved.
To me, it could be. To me, the most exciting stuff, again, is the stuff that's hard to think about. But one that I get really excited about is I love knowledge. I like understanding how the world. Most people do, right?
That's what we do.
That's right. We're
machines that do that.
Exactly. That's the hallmark of us is our species is that we're the only ones who've ever built a model of the world and the universe. We're the first animal that ever understands there's a thing beyond our own immediate environment. Yeah. And we've discovered the laws of physics. I mean, this is an exciting thing to do. We get a thrill of it. So I would love to accelerate the accretion of knowledge.
Yeah, I like that.
And we can build machines that are tools for humans, not replace humans.
Right.
There's nothing to do about replacing us.
Right.
Machines that are tools for humans to help us accelerate our science. And
that's what we do. We build tools.
Yeah.
We tell stories. We understand things. We learn.
And we use computers today. Computers help scientists all the time, right? They help us understand the world. The internet is the best thing for learning about the world.
Right.
So we can build intelligent machines that accelerate our accretion of knowledge. We'll understand the world and more about it. And that, to me, is an exciting future. I mean, I want to understand the end game. How did this whole universe get here?
Yeah.
What's going to happen in the future? And, could we do that in my lifetime? I don't know. If we could get there sooner, we might. But if we had really, imagine we had mathematicians and physicists that ran a million times faster than a human and never got tired and never wanted to have sex and never got, bored. And that's all they did. They just thought about theories.
Michio Kaku says we're close to a unified field theory. Just a little push.
I'm hoping he's right. I'm hoping he's right. But
he says it's a bubble bath before the Big Bang. It's just a bubble bath. I don't understand it, but
yeah.
Maybe we'll know.
As a casual observer, maybe slightly more than casual observer, is that there's always this feeling that you're right on the threshold of the next thing. We know once we get the atom, once we get the first level. Once we discover the horizon of the universe, there's always more. I mean, it's just amazing how surprising the universe has turned out to be. It's just incredible how big it is and how small we are and how limited it seems. And so, we're pushing the abilities of humans in terms of our ability to discover this stuff, not to understand it. We can understand anything. Yeah. But I think we can make tools that really help us discover the future. And, it might sound trite, but even Grok, our simple little product, 1,000 of the mouth neocortex, is discovering structure that we've already proven that it's discovered structure that humans can't see.
What I find exciting is we've tried so many times, we've beat our heads against the wall of artificial intelligence so many times, and here's something that actually works. Yeah. Here's something it's a baby step, but it's actually doing it.
We got a framework for how to build this whole thing out, so I'm not saying we're there yet, but I can see how it's going to play out.
Very exciting.
I can see how it's going to play out. And we've made some pretty major progress on this.
Numenta.com, On Intelligence is the book.
Can I put a plug for something else?
Please, yes.
Our open source project called NuPick, you can find that at numenta.org. So we've taken all these learning algorithms that we use in Grok and elsewhere, and we put them in an open source project. We started that last summer, and it's off to a great start. If you're really interested in this stuff, there's
I'm on the GitHub page right now.
Very
it's
active
really exciting.
email lists.
Yeah.
I participate in the theory side there, so I'm every day pretty much contributing. And so this is a good place if you want to sort of take this. Can I tell you another little story here?
Sure.
There's a company in Austria called CEPT, CEPT.au, I think it is, for Austria. And they read our white paper about how these algorithms work, and they built a tool built on top of that about natural language processing, built on the same principles of these sparse distributed representations we were talking about earlier.
CEPT.
I'm sorry, AT.
Yeah.
AU is Australia.
Right.
Yes, AT, CEP.
The cortical engine for processing text.
Yeah. And you should see, I have in some of my talks, the more recent ones, I give a little demo of this thing. We should watch that. Because it's amazing stuff that we can starting to do with language using sparse distributed representations.
Wow.
These guys are really cool. We're combining their stuff with our stuff.
That's great.
So this is the beginning. I'm telling you, Larry, this is the very, very beginning of what I think is machine intelligence. What's going to play out? We're in that. In 1940, we entered 1940 with the sort of the concept of the universal Turing machine,
right.
And we ended in 1940 with the computing industry. We are in that phase right now. We have the basic theories and concepts. You can read about them and watch my talks. You can look at the code. It's not easy, but once you get it, it's pretty cool. And then we're in that period where we're just starting to figure out how to build useful things, and we're starting to emerge into an industry. I think we're just on that cusp right now, and I think with Grok, we've really turned a corner there.
Very exciting. Numenta.org if you want to get involved in the open source project. I'm sure there's some programmers out there who'd love to start playing with this. What an interesting idea. Jeff, such a pleasure to see you again. I think we're very fortunate that you've devoted your energies to something so exciting.
Well, thank you.
Yeah, I think
it's
we'll all
fun.
benefit. Yeah, and it's fun.
It's fun, and I think it's important. So,
I think you might be right.
So, what else we can do in our life, right?
Exactly, exactly. Build a tool. That's what we do here on this planet. We do triangulation now at 11 a.m. Pacific. That's 1800 UTC, 2 p.m. Eastern Time on Mondays. Always great, always interesting, and I think your brain will always grow if you watch. Make sure you subscribe at twit.tv/TRI or wherever you get your netcasts. Thanks for joining us. Thank you, Jeff Hawkins, and we'll see you next time on Triangulation.